It is not hiding in Andromeda, 2.5 million light-years away from us tonight. It is not hiding on Mars, or in the clouds of Venus, or anywhere inside our own solar system. It is hiding 13.4 billion light-years from Earth, in light that left its source before our planet even existed. And when the James Webb Space Telescope finally caught that light, it broke a rule scientists thought was almost bulletproof. No guessing, no dramatizing, just facts, real telescope data, and real scientists arguing about what it means. If you want to actually understand this discovery before the algorithm buries it under 100 watered-down explainer videos, hit subscribe now, because we are about to walk through every number, every objection, and every reason this story is still not settled. Here is the short version before we go deep. Webb looked back toward the very beginning of the universe and found galaxies that were already big, already bright, and already packed with mature stars, at a point in cosmic history when, according to the leading model of how the universe grows, they should have barely started forming. One of them, a galaxy called GN-Z11, is seen as it looked just 430 million years after the Big Bang. Another set of galaxies, spotted in 2023, appear to already weigh as much as 10 billion suns, at a time when the universe was only about 600 million years old, which is roughly 4% of its current age. We are going to explain why that number is such a problem, what tool actually caught it, which parts of this story are rock solid, which parts are still being fought over in scientific journals right now, and what you can actually do with this information once you know it. We will also walk through a strange twist that most coverage of this topic completely leaves out: a hidden population of objects that looked like overgrown baby galaxies at first glance, but turned out to be something else entirely once scientists looked closer. To understand why this is strange, you first need to picture the universe as a slow cook, not a microwave. After the Big Bang, matter was spread out almost evenly, like flour scattered thin across a huge table. Gravity is patient. It pulls small clumps of matter together first, then those small clumps merge into bigger ones, then those bigger ones merge into galaxies, over hundreds of millions and billions of years. That is the mainstream model, called lambda CDM, and it has correctly predicted an enormous amount of what we see in the universe for decades. Under that model, 600 million years after the Big Bang is still early morning. It is nowhere near enough time to bake a galaxy the size and weight of the Milky Way. The tool that caught this is the James Webb Space Telescope, and the trick it uses is almost embarrassingly simple to explain. Light from very distant, very old galaxies gets stretched out on its long journey to us, the same way a siren sounds lower in pitch as an ambulance drives away from you. Visible light gets stretched into infrared light, wavelengths our eyes cannot see, but Webb's instruments are built specifically to catch. The more the light is stretched, a number astronomers call redshift, the further back in time you are looking. Webb's main camera, called NIRCam, and its spectrograph, called NIRSpec, are precise enough to take that stretched infrared light and read it like a fingerprint, confirming both how far away a galaxy is and roughly what it is made of. Hold on to that word, redshift, because it becomes the center of the entire fight later in this story. Webb itself is built specifically to catch light this faint and this old. Its main mirror measures 6.5 meters across, built from 18 gold-coated hexagon segments that unfolded in space after launch, giving it more than 6 times the light-collecting area of the Hubble Space Telescope that came before it. It sits almost 1 million miles from Earth, at a stable gravitational parking spot called the second Lagrange point, riding behind a sun shield the size of a tennis court that keeps its instruments cooled to nearly 400 degrees below 0 Fahrenheit. That extreme cold matters enormously, because infrared light is essentially heat, and any warmth from the telescope itself would drown out the faint infrared glow of a galaxy sitting 13 billion light-years away. Every discovery in this video only exists because engineers solved that cooling problem well enough to let Webb listen for a whisper across the entire width of observable space. Have you ever personally witnessed something that made you stop and question what you thought you understood about the world? Tell me in the comments what it was and how it felt at that moment. The first case study is GN-Z11, and it is the closest thing this story has to a celebrity. Spectroscopy, meaning Webb's detailed light fingerprinting, confirmed this galaxy exists at a point just 430 million years after the Big Bang, making it one of the earliest galaxies ever directly confirmed, rather than just guessed at from a photograph. What makes GN-Z11 strange is not just how early it is how developed it looks for its age. It shows signs of unusually vigorous star formation and chemical fingerprints you would expect from a galaxy that had already been cooking for a much longer time. Finding a toddler with the muscle mass of a teenager is not impossible, but it makes you ask serious questions about what accelerated its growth. The second case study is bigger, and this is where the real argument in astronomy started. In 2023, a team led by researcher Ivo Labbé published a discovery of a population of candidate massive galaxies dated to roughly 600 million years after the Big Bang, each one estimated to weigh in at over 10 billion times the mass of our Sun. 10 billion solar masses is not a small galaxy. That number puts these objects in the same weight class as fully grown galaxies that, under the standard model, should have needed several billion more years to reach that size. When this paper landed, it did not quietly sit in an academic journal. It set off alarm bells across the entire field of cosmology, because if the numbers held up exactly as published, it meant either galaxy formation works far faster than anyone assumed, or something was wrong with how we were measuring these galaxies in the first place. This is where the story gets more honest than most videos about it. A follow-up paper, published by researcher Peter van Dokkum and other collaborators, carried the blunt title, Confirmation and Refutation of Very Luminous Galaxies in the Early Universe. Read that title again. Confirmation and Refutation, in the same paper about the same category of objects. Some of the extremely bright early galaxies that first excited astronomers turned out, on closer inspection, to be something else entirely, sometimes closer, sometimes less massive than first thought, sometimes even active supermassive black holes lighting up their surroundings and mimicking the glow of a young massive galaxy. Science does not get more transparent than a paper that openly confirms some claims while tearing down others in the same breath. Then, in 2024, the record got broken again, and this time the evidence came with almost no room for doubt. A galaxy called JADES-GS-Z14-0, studied by a team led by researcher Stefano Carniani, was confirmed sitting at a redshift of about 14.18, which works out to roughly 290 million years after the Big Bang, only about 2% of the universe's current age. That alone would make it the most distant confirmed galaxy ever measured. What happened next made it even stranger. Using a separate telescope called ALMA on the ground in Chile, two independent research teams both detected oxygen inside this galaxy, an element that is not supposed to exist yet in large amounts this early, because oxygen only gets created and released once earlier generations of stars have already lived, burned through their fuel, and died. Finding oxygen already spread through a galaxy this young is like walking into a newborn's nursery and finding a fully stocked kitchen. Researcher Sander Schouws, who helped lead one of the two oxygen detection teams, described the discovery as comparable to expecting to find only babies, and instead finding someone already grown into their teenage years. Carniani himself said the result genuinely surprised his team and reopened questions about exactly when and how galaxies first came together. Follow-up imaging also showed this particular galaxy stretches over 1,600 light-years across, and gets its light mostly from young stars, rather than from a feeding black hole, which rules out one easy explanation and leaves the fast, early maturity itself as the real mystery still standing. Which of these possibilities scares or fascinates you more? A universe that grows galaxies faster than we thought, or a universe where our instruments have been fooling us the whole time? Drop your answer below. The plot thickens further once you bring in a different piece of Webb's hardware, an instrument called MIRI, the mid-infrared instrument, which sees even longer wavelengths of light than the main camera used in the first wave of discoveries. When astronomers went back and re-examined some of these early massive galaxy candidates using MIRI data, the mass estimates for several of them dropped by roughly a factor of 2.5. That is not a rounding error. That is the difference between a genuine crisis for our best model of the universe and a more ordinary story about scientists initially overestimating how much material was packed into a very distant, very hard-to-measure smudge of light. Recent survey work looking at 36 massive galaxies in this early era found that most of them actually fit comfortably within the standard model once properly measured, with only a small handful of truly extreme cases still standing out as genuinely hard to explain. But a small handful is still not zero, and that handful is the real heart of this mystery. Even after the corrections, researchers identified around 3 galaxies from this early population whose stellar mass estimates stayed stubbornly high, in some cases exceeding 100 billion solar masses, an amount of mass that, if it is real, would require these galaxies to have converted roughly half of all their available raw gas directly into stars. For comparison, our own Milky Way, over its entire 13 billion year lifetime, has only managed to convert a small fraction of its available gas into stars. Something in the early universe, in these specific rare cases, appears to have run its stellar factories at an efficiency almost nothing nearby comes close to matching. Researcher Michael Shao and collaborators working through the FRESCO survey found that even after this correction, a handful of these ultramassive objects genuinely still hold up under close scrutiny, meaning the mystery narrowed dramatically without disappearing completely, which is exactly the kind of nuanced, half-resolved result that never makes it into a sensational thumbnail. Then there is a second layer to this puzzle that most competitor videos skip completely because it does not fit a simple headline. In 2023, researcher Tobias Lusser and collaborators identified a galaxy that had already gone quiet, meaning it had stopped forming new stars almost entirely, at a cosmic age of only about 700 million years. Picture a bakery that opens, produces an enormous batch of bread in record time, then shuts its ovens off completely, all within the first few months of being in business. A galaxy is not supposed to burn out that fast this early in cosmic history. Finding one that already had, on top of finding galaxies that grew unusually big, unusually fast, suggested early galaxies were not just growing quickly, they were living entire, fast, dramatic life cycles, compressed into a sliver of the time we expected them to need. Layered on top of both of those puzzles is a third one, involving shape rather than mass. Multiple research teams, including work led by Leonardo Ferreira and Brant Robertson, found that a surprising number of these early galaxies already show flat, rotating, disk-like structures, similar in basic shape to our own spiral Milky Way. Under the older picture, built mostly from Hubble Space Telescope images, galaxies were expected to look like a chaotic, clumpy mess for a long stretch of early cosmic history, before eventually settling into neat, spinning disks. Finding orderly spinning disks this early is like discovering a newborn who can already ride a bicycle. It does not break physics outright, but it forces you to rethink how quickly order can emerge out of a young, violent, expanding universe. Older Hubble images simply were not sharp enough or deep enough in infrared light to catch these shapes clearly, which means part of this puzzle was always sitting there unseen, waiting for an instrument with enough resolution and enough patience to finally bring it into focus. What is one question about this story you have never seen anyone actually answer? Write it below and I will read through the comments and pin the best ones. There is a fourth layer to this mystery, and it might be the strangest one of all. Scattered across Webb's deepest images, astronomers kept finding small, extremely red, extremely compact objects that did not look like ordinary galaxies at all. Researchers nicknamed them little red dots, and the first one, confirmed through detailed spectroscopy, a source called CEERS 746, was measured sitting at a redshift of 5.624, meaning we are seeing it from deep in the early universe. When teams like the one led by researcher Dale Kosevsky studied the light coming from these little red dots closely, they found broad, smeared-out spectral lines, the exact kind of signature you get from hot gas whipping around at extreme speed near a black hole. In other words, many of these dots were never ordinary baby galaxies at all. They were rapidly feeding supermassive black holes, dressed up in enough dust and gas to look, at first glance, like something else entirely. There is one more number worth sitting with before we move on, and it is not about any single galaxy, it is about how many of them exist. Multiple survey teams, including researchers Yuichi Harakane and Rebecca Bowler, counted up the bright galaxies Webb was finding at redshifts beyond 10, and compared that count against what standard galaxy formation models predicted should be out there. The surveys kept finding a genuine excess, meaningfully more bright early galaxies scattered across the sky than the models expected, not just one or two unusually large outliers, but a broader population showing up more often than the math said it should. A single strange object can always be written off as a fluke or a measurement error. An entire population showing up more often than predicted is a much harder pattern to explain away, and it is one reason this remains a live argument inside cosmology conferences rather than a solved footnote. This single discovery reshapes a huge chunk of the earlier story. Some of the objects that first fueled the impossible early galaxy panic may not have been overweight galaxies at all. They may have been black holes glowing so fiercely that survey instruments mistook their light for the combined starlight of an entire massive galaxy. One particularly strange black hole found this way, nicknamed Virgil by the same researcher, sits paired with a companion object nicknamed Cerberus, and both show mass estimates that are startlingly large for how early they appear in cosmic history, forcing astronomers to ask how a black hole could grow so heavy so fast without violating the normal speed limit on how quickly matter can fall inward and feed it. Stranger still, when astronomers checked these little red dots for X-ray emission, the kind of radiation almost every nearby feeding black hole gives off, most of the little red dots stayed nearly silent, producing far less X-ray light than a normal active black hole should. Nobody has fully explained yet why these early black holes are so bright in infrared light and so quiet in X-rays at the same time, which means this piece of the puzzle is not solved either. It is simply better mapped than it was 2 years ago. Follow-up survey work using Webb's slitless spectroscopy mode found roughly 20 of these little red dots, showing the same broad hydrogen signature in a single targeted search, meaning this is not one strange fluke object. It is an entire hidden population that earlier surveys never had the resolution to separate from ordinary early galaxies. So where does that leave the actual explanation? Because this is the part where honest science stays messy instead of wrapping up in a neat bow. One leading idea is called bursty star formation, argued by researchers including Guoqiao Sun and Charlie Mason, which suggests early galaxies did not grow steadily, they grew in short, violent bursts, briefly outshining their true average brightness and making surveys catch them at their most flattering, most exaggerated moment, similar to only ever photographing a sprinter mid-stride and assuming that is their resting walking speed. A second idea involves the mix of stars being produced, sometimes called a top-heavy initial mass function, meaning the early universe may have preferentially built unusually large, unusually bright stars, rather than the more balanced mix of star sizes we see forming today, which would make young galaxies look far more luminous for their actual total mass. A third idea is simply higher raw efficiency, meaning early gas clouds under the right pressure and density conditions may have genuinely converted a larger share of themselves into stars than gas clouds do today, without needing any new physics at all, just different environmental conditions. Think of it like an oven that runs hotter and faster in a much denser, more compact kitchen, producing more finished loaves from the same amount of raw dough, simply because the conditions around it were more extreme than anything we can study nearby today. A fourth and far more radical explanation gets floated by a smaller number of researchers, the idea that something about early universe cosmology itself, the actual rules governing how fast structure can form, may need slight adjustment. Researcher Michael Boylan Colchin was among the first to formally stress-test the Standard Model against these early massive galaxy claims, and his early analysis helped set off the whole debate by showing just how tightly stretched the standard picture becomes if the biggest mass estimates turn out to be correct. This is the explanation you will see splashed across the most sensational headlines, the one implying Webb broke the Big Bang. It is important to say clearly that most working astronomers currently favor the more boring explanations: bursty star formation, unusual stellar populations, measurement error, and black hole contamination, over the idea that our fundamental model of the universe is broken. But it is also important to say clearly that the option has not been ruled out completely either, and that is exactly why this remains one of the most actively debated open questions in modern astrophysics, rather than a closed case. Have you ever felt genuinely unsettled by how much scientists still do not know about something you assumed was fully figured out? Tell me what it was in the comments below. Zoom out for a second and notice what actually happened here across just a few years. A single space telescope forced multiple independent research groups to publish papers confirming, then partly refuting, then remeasuring, then reconfirming claims about the same population of ancient objects. That is not a sign of a broken field. Fields that cannot correct themselves in public are the ones you should actually be worried about. The back and forth you just heard, crisis, correction, new twist with black holes, new record with oxygen, is what a healthy, functioning scientific process looks like when it runs into something it did not expect, out loud, in real time, for anyone willing to actually read the papers instead of just the headlines. Given all of that uncertainty, here is what you can actually do with this story, starting this week, without spending a single dollar or buying any gear. First, before you believe a headline about any space discovery, look for the word spectroscopy versus the word photometric. Photometric redshift is an early estimate based on color and brightness alone, and it can be wrong. Spectroscopic redshift, like the conformation behind GN-Z11, is a much more solid measurement based on detailed light fingerprinting, and it deserves far more trust. Knowing that one distinction alone will let you spot shaky claims faster than most casual science readers online. It is the same distinction that separated the shaky early estimates for those 2023 massive galaxy candidates from the much more solid, spectroscopically confirmed record set later by GN-Z11 and JADES-GS-Z14-0. Second, wait for replication before treating a single paper as settled fact, especially in a fast-moving field like this one, where new instruments keep changing what counts as solid evidence. The story of the 2023 massive galaxy candidates is the perfect lesson here, because the very same category of objects that made global headlines was partly confirmed and partly refuted within the same research process, sometimes by the same authors. One paper is a claim. Multiple independent teams reaching the same conclusion with different instruments is much closer to a fact, and that difference matters every single time you see a bold space headline online. Third, go find one primary source instead of only reading secondhand summaries, since the original release almost always includes the exact numbers and the exact amount of uncertainty that gets quietly dropped by the time a story reaches your feed. NASA, the European Space Agency, and the Space Telescope Science Institute all publish plain language releases about Webb's findings directly on their own websites, written specifically so a curious non-scientist can follow along. Reading even one of those directly, just once, will make you noticeably harder to fool by exaggerated video titles going forward, including titles very similar to the one on this very video. Fourth, get comfortable holding two ideas at once. This discovery is genuinely real and still genuinely unresolved, and neither half of that sentence cancels out the other. It is tempting online to want a clean, dramatic, final answer. Either Webb broke physics or it did not. The honest answer right now is that some early tension has genuinely eased with better data, while a small, stubborn handful of cases still resist easy explanation, and both of those things are simultaneously true. Learning to sit with that kind of unresolved complexity is a genuinely useful skill for understanding real science instead of just science headlines. Fifth, keep a small list of the specific unresolved cases mentioned here: the ultramassive outliers, the quiescent galaxy found at 700 million years, the unexpectedly disk-shaped galaxies, and the little red dots still puzzling researchers with their silent X-ray signatures. Science updates on exactly this topic land every few months as more data comes in from deeper Webb surveys. Checking back on a short list of open questions is a far better habit than chasing whatever new space headline shows up in your feed that week. Sixth, notice the difference between a paper being published and a paper being confirmed. The little red dot story is a perfect example. First they looked like galaxies, then closer study revealed many were probably feeding black holes instead, and now researchers are still arguing over why those same black holes barely give off any X-ray light at all. That is not scientists failing, that is scientists correcting themselves in public, one honest step at a time, which is exactly what you should want happening behind any claim you decide to trust. Seventh, remember that skepticism and wonder are not opposites, no matter how often online arguments make them feel that way. You can hold on to genuine awe about a 290 million-year-old galaxy already carrying oxygen, while also demanding solid spectroscopic proof before you accept the next headline claiming something even more extreme. The scientists at the center of this exact story do both of those things simultaneously, every single week, and that combination is exactly what separates real curiosity from either blind hype or reflexive dismissal. That habit of checking before sharing is a small thing, but it compounds fast once you start doing it consistently on every big, exciting science headline you come across from now on. If a strange, unresolved discovery like this one reached your own curiosity out of nowhere tomorrow morning, what would your very first move be to actually verify it? Walk me through it in the comments. Let's pull the whole story back together with the numbers that actually matter. GN-Z11 sits at 430 million years after the Big Bang, spectroscopically confirmed, genuinely one of the earliest galaxies ever directly measured. JADES-GS-Z14-0 pushed that record even further back to roughly 290 million years after the Big Bang, already carrying oxygen it should not have had time to make yet. The 2023 massive galaxy candidates were estimated at roughly 600 million years after the Big Bang, with masses over 10 billion suns. numbers that triggered a real crisis, followed by real correction, once longer wavelength MIRI data came in and cut many of those mass estimates by more than half. A small number of truly extreme cases, requiring close to 50% star formation efficiency, still remain difficult to fully explain today. A quiescent galaxy already finished with its main growth spurt was found at just 700 million years old. Multiple teams have spotted flat, orderly, spinning disk galaxies far earlier than expected, and an entire hidden population of little red dots turned out to be feeding black holes, glowing brightly enough to fool early surveys into thinking they had found overweight baby galaxies instead. None of that means the universe is broken, and none of it means scientists were lying to you or secretly hiding something from the public. It means real science is messier, slower, and far more honest than a single dramatic headline can capture, and that messiness is not a flaw. It is the entire point of how real discovery works. Every one of us watching this tonight is looking at light that left its source before humans existed, before Earth existed, in some cases before most of the atoms in your own body had even been forged inside a star. That is not a small thing to sit with for a moment, and it should feel less like dread and more like genuine wonder that we get to ask these questions at all. Think about how strange this timeline actually is. That light started its journey 13.4 billion years ago, crossed almost the entire width of the observable universe, and finally landed on a gold-plated mirror parked 1 million miles from Earth at the exact moment in history when humans finally had the tools to catch it and read it. A few hundred years earlier, and nobody could have built the instrument. A few hundred years later, and maybe someone else does this exact video with better data and cleaner answers. Right now, tonight, we are the generation standing at the edge of that specific window, watching the universe's baby pictures develop in real time, arguing over what we see the same way any family argues over a slightly blurry old photograph. We are not done with this story, not even close, because more data is landing from deeper web surveys every few months, and at least a few of today's open questions should have clearer answers within the next year or two. Somewhere out there, a research team is right now pointing Webb's mirror at another faint red smudge, waiting weeks for enough light to gather into something readable, hoping this next one settles an argument instead of starting a new one. That is the actual pace of real discovery. Slow, careful, occasionally thrilling, nothing like the instant certainty a flashy title promises you. When that update lands, we will walk through it exactly like we did tonight, number by number, source by source, no shortcuts, no manufactured mystery, just what the evidence actually shows. Stick around for that, because the universe is not finished surprising us yet, and honestly, neither are we.